to close the day with once again with an award winner. We've had several today. Fantastic. And I'm definitely looking forward to listen about your story and the exoplanets side of the whole thing, which I wonder what it is.
Yes, well.
Thank you.
Stage is yours. You have the pointer. Guys, thank you very much.
Thank you. Thank you. Pleasure.
But thank you.
Well, thank you for the invitation, first of all.
It's our pleasure.
Thank you. And thanks everyone who is attending. So now we are going to make a switch from data science to data science fiction. And can we see the slides? Yep. It's a slight technical problem, but should be solved now. Okay, so I'm Luís Simões. I'm lead data scientist at ML Analytics, and I'm going to talk to you about a competition that was put forth this year by ESA's ARIEL mission. First, a slight introduction to us. We are a data science boutique established in 2018. Over the years, we have created many models for different clients, you see on the left, and right now our models are generating predictions for around 5 million individuals every month. So statistically speaking, many people in the audience probably have already been processed by our models. And before delving into the competition itself, just a slight background, because the victory in the competition is not something that comes out of the blue. It's the result of many years of work in the space sector doing artificial intelligence projects. And I would like to first showcase a few of these projects that I developed also as a way to show the artificial intelligence that is being developed in space. So at some point, I developed the IPSIS piloting software to autonomously land spacecrafts onto planets with autonomous hazard detection and avoidance. You see on the left an example of the software, which right now made a retargeting to a safe space spot because the original target location was not safe. This was a very interesting project developed for Airbus and ESA. And after this project, I joined the Advanced Concepts team of the European Space Agency, which is the agency's internal think tank that is tasked with being the first to identify trends in science and technology that could be disruptive to the space sector in the years ahead, and is tasked with being the first to develop the internal projects. While with the group, I did research in many areas, especially in spacecraft trajectory optimization. Also, we developed an experiment for the International Space Station. And at some point, we won something very interesting, a Gold UMIS Award, a prize that recognizes the artificial intelligence work that attains or surpasses the human capacity in a given problem domain. It was awarded to a mission that we developed to explore the moons of Jupiter. Later on, I was a member of the Frontier Development Lab, which is NASA-ESA research accelerator to foster the introduction of artificial intelligence into the space sector. I had a very interesting project. The image you see on top is the software that spacecraft operators use to book communications between spacecraft of a constellation and the ground stations on the ground. And we were given 10 years of operational data like this, and we had the privilege of training machine learning models to automate the decision-making process of the operators, because we are about to enter into a future where constellations don't have 4 satellites like the one we see here, but they have tens of thousands, in some cases, of satellites, and there's the need for automated decision-making processes. Now, jumping to the mission, ARIEL is going to be a mission launched in 2029, and it's going to tackle this problem. So we are looking at the light coming from a star, and when we see a dimming of the light curve, we infer a planet, an exoplanet that is passing in front of it. And as you just saw from these 2 examples, different planets affect the light curve in different ways. And just by studying the shape of the light curve, we can infer a lot about the planet that is passing in orbit of this star. And Oh, sorry. Okay. And it's fascinating that we are barely able to perceive that a planet is in the orbit of a star, but by carefully studying these light curves, the mission is going to work out the chemistry, temperature, cloud coverage, wind speeds, climate, and much more of the planet. And how can it do this? Because it's going to distinguish between photons of light coming directly at us from the star, from those that cross the planet's atmosphere. And as they were crossing the planet's atmosphere, they interacted with whatever is in there, and light changes. And it's very interesting that the mission acknowledges, very humbly, that to properly analyze the data to the accuracy that is needed to achieve the scientific goals of the mission, astrophysics currently does not have in-house the tools to do that. Artificial intelligence does. So they created this competition as a way to bring experts from the worldwide community who could put their tools to the task and see what would come out of it. Here we see already some of the real data from the competition. So we were given synthetic data that simulates the data that will be captured by the sensors in 2029. And the gray lines you see on the left, they are the light curves that actually reach us. So very different and very chaotic compared to what we saw before in the video. But let me tell you that what's on the left is actually one of the simplest cases that we have. Because with just some simple data pre-processing techniques, those gray lines turn into the green one. And it's very easy to read from it the actual target that we want, so the actual size of the planet. It becomes much more challenging when we go to examples like the last two, because sometimes the signal seems clean, but actually the light curve is pointing us in a very different direction from the real target. And then there are cases where the data is just completely chaotic, and even a human expert looking at those clean data sets already cannot infer what's going on. But without inferring this red line, the mission cannot achieve its scientific goals. So, there was a previous competition in 2019. This was the second edition and last one for the problem of this kind. And what you see here in this plot is the progress that was achieved in between the two editions, the 2019 to my solution now. And to achieve its scientific goals, the mission has a desired precision of 10 to the minus 5, which is here in this black line. So a lot of progress has been made. We are already within the error, the order of magnitude of the error, but still some room to go. And after the previous edition, the organizers and the top teams published a very interesting scientific paper with the description of the approaches that had success in tackling this problem. And this, I'm not an astrophysicist, far from it. So this was my first contact with the problem, and where I could see already some techniques that work and others that don't. And something very interesting I realized is that there was essentially a technical tie last time around. And there were very distinct approaches in the top of leaderboards. So there were some that were deep learning, state-of-the-art, the very hyped approach nowadays. But there were next to it, while deep learning approaches would take 30 hours to train a model, there were approaches that were training linear models on top of properly engineered features, and they would do the work in milliseconds. So I took those insights into my approach, and I tried to do something that would bring the best of both worlds into my model. And my model, in the end, is not deep learning, but all the other models in the top 5 this year, they were. So I will be, there was a lot of work that went into this model. There's no time to cover everything. I will just be providing a few of the ingredients that enabled success in the competition. One of them is that I developed a custom modeling approach to tackle this problem. So there's probably no need here, but a brief overview of how these approaches work. If you're doing deep learning models, then you can imagine that your data resides in a high-dimensional space, and you are training a neural network so that as data flows from its input layer to the target, the data is gradually unfolded until you are finally reaching a state where, well, the target is very readable. But this is the state-of-the-art for several kinds of problems, images, video, time series, and it's something that is the obvious choice for the kind of problem that was in this competition. But it's very costly to train these intermediate layers. That's where a lot of work happens during the training. There's another approach that is not as much in the news nowadays, but is the state-of-the-art. So if your data can be properly represented in an Excel sheet, then probably it's already structured, and what you want to deploy in it is not deep learning, but gradient boosting. And gradient boosting is an approach that combines multiple weak learners into a strong one. So here in this demo, you see that different decision trees that by themselves have limited modeling capacity. They can only learn these rectangles, but by combining their multiple predictions, suddenly we are learning this complex spiral shape. So my modeling approach, first of all, took what's called an extreme learning machine. It's a kind of neural network, but not the usual kind. Concretely, it is not trained through backpropagation. So the data is going to be fed in through an input layer. There's a single hidden layer, and this hidden layer, its weights are randomly defined at the start, and they remain fixed. So you rely on random expansions into a higher dimensional space. And then you train a linear model. So this is where the linear model of the other teams comes into approach in mind. You train a linear model, which trains very fast. And what happens is that by training a model over this enlarged feature space, what actually you are doing is that you're learning a nonlinear model in the original space. And this can enable a very, very fast training of effective models. And the interesting thing is that because these models train so fast, we can afford to ensemble many of them. In the competition, my base model was an extreme learning neural network with only 300 hidden layer neurons, and this could train over the competition's train set, which has roughly 15 gigabytes of data, in only 500 milliseconds on a laptop CPU, so not even specialized hardware. It's affordable to ensemble many of them, so I assembled 300, and this could be done in 2 minutes and 30 seconds, which compares very favorably with the 30 hours of the other teams. In total, this led to a modeling approach that learned 17 million parameters. And it's crucial, this last aspect, which is the fast iteration time means that it's easy to test new ideas. And early on in the competition, 1 in 3 ideas would lead to improvements in the model, but later on, diminishing returns, it gets progressively harder, and at some point, maybe 1 in 10 or 1 in 20 ideas works. And if you are relying on a modeling approach that takes 30 hours every time, you are not going to try as many things. So to some degree, the success in the competition came from my capacity to come up with ideas, train them, test them, and see which ones worked. Next, another ingredient for success was an alignment of model and problem objectives. Because the organizers gave us this equation here, through which they were evaluating models and assessing which ones were the best. And when you look at this equation and you know the data that you're dealing with, you realize that the traditional loss functions for which models optimize, square loss, absolute loss, they would lead to something that is not really optimizing for the competition's objective. So something I came up with was that I created a custom version of the Huber loss function, so that through gradient boosting, I would train models that would align closer to what the organizers were looking for. And then, maybe the most important part for the success in the competition was the feature engineering process, which was extensive, and I will only cover a bit of it here. But it's the process of taking in the raw data and engineering the features so that they represent the reality that needs to be modeled. And through the work while doing the feature engineering, I noticed two key trends. One I call the strength of weak features, which is interesting because the data that we were handling, the raw data, is extremely noisy. And it's therefore important to eliminate as much noise as possible, but only to a certain extent, because there's systematic noise, and the model benefits from being exposed to it so that it can learn how to properly cancel that noise. So I had to find the sweet spot where data was clean, but not completely clean, so that the model could take the most benefit from that data. And then the other is the importance of staying in the same domain. I found many, many kinds of features that have predictive power in this problem domain, but surprisingly, sometimes I would add them to the model and performance would degrade. Remember that we are here dealing not with the usual problems in which we are happy with some level of accuracy. Here, this model had to have no error. And I noticed that it was important that I would find a set of features that work well together. And these features individually might not be the most predictive, but I had to find a sweet spot where they were complementary and easy to process and aligned with the prediction target. This is an overview of the final training set I came up with from the raw data. And we are looking at the mean and standard deviations, the feature values across the whole train set. And the features are divided in 4 blocks. So first, the star and planet parameters that were given in the data set. So in addition to the observations that are being done of the star, there are some other parameters of the planet and the star that are known and were useful, very useful. Then a quadratic means over the full time series of relative fluxes. This is an adaptation of the absolute energy feature to make it more consistent with the other features. Predictions of second degree polynomial fits for the central time step, where you expect the maximum dip in the light curve to be. And finally, and mainly, the 4th large group you see there, which was an observation grid of harmonic means over overlapping time windows. And what this means, I will show here, is that after all the data processing, those chaotic curves you saw in the beginning, data could be expressed in this form. And you have here the prediction targets that we had for each time series. So as you see, there's still a lot of noise here. They are very chaotic in some cases, like especially this one. And the model had to look at this data and perceive the values in these horizontal red lines. It's hard to see here. I hope it's easier at home. But I did not give the model the full time series. After computing these values, I took only these grid of values, and the model would only be exposed to the values in this grid for 55 different wavelength channels. And this is the training data, and I'm happy to show that the green line is what the model predicts for these planets. So this is during cross-validation. So the planets that are being shown here, they were not being used to train the models. But when we fed the planets' data through the model, we see that the green lines align very, very well with the red lines that were the prediction targets. And it was challenging here, and it was even more challenging in these other examples, because I would like to know what's going on here. I need to talk to some astrophysicists, because there are cases where at different wavelengths you perceive the planet to be of very, very distinct sizes. And then you had those cases I mentioned previously where the data seems clean, but actually it's not. It's being affected by something called the persistence noise in the sensor, and the true targets are far away. And even in these very challenging cases, we see that the model very correctly predicted the targets. And that's what I wanted to bring and show to you. There will now be further developments in this work. And a month from now, we will be in London discussing with the mission exactly how to bring this model forward. And I hope you enjoyed it. And if you have any questions.
Luís, my question to you is, What question can I have? What should I ask you?
Well, there's a very interesting question, which is, in data science, we fear concept drift, right? So we fear when we have a model in production and suddenly the model is being exposed to a different reality. But for a mission, concept drift is exactly what they would love to see, something that science has never seen before. And if we move into a future where artificial intelligence algorithms are being used to power these missions, we need to ensure that when a model makes a prediction, it's something that we can trust and it's not just garbage. So that's where most exciting work will be, I think, in validating these models.
Very good question, and above all, very good answer. Thank you very much.
Thank you.
It was not for no reason that we invited you to close today, because we kind of scaled it all up since the very beginning. We started talking to students in the morning. We had a debate on where do we stand as a country, as an ecosystem, the companies, the talent. We spoke about so many different dimensions. Then we evolved. We spoke about different client cases or use cases, etc. And we wrapped the day with a tremendous demonstration that there's a use and a future and a challenge and a world to know because of this area of knowledge, of expertise. Thank you so very much.
Thank you.
It's really exciting to go through, not to understand everything. I was far off quite some times, but I'm very glad we invited you to be here with us today.
Thank you very much for the invitation.